All right, here we're going to take a look at how to create end releases in frame elements. And in other words, it's how to create a joint in between frame elements that share a common node. For example, it could be a hinge type joint. All right, well, let's go ahead and take a look at the first method, or one of the methods that we could create a joint. Now, this isn't an end release. This would be creating something called an MPC, or a multi-point constraint, which is where we have two elements that usually share coincident nodes, but they are not the same node. And between those nodes, there is a constraint such that one of the nodes, or the movement of one of the nodes, depends on the movement of another one of the nodes. Specifically, you'll have independent or dependent degrees of freedom. And so, for example, if we have nodes A and B, we might say that the behavior of node B, or node B's movement in the y direction, depends on how node A moves in the y direction. So that might be an example of a multi-point constraint. Another option is using something called a bushing element. And so this would be called a C-bush element in Nastran. And so we still have two elements with usually coincident nodes, but not the same node. And we just introduced a spring element that has stiffness in multiple directions. So this is our bushing element, provides stiffness in various degrees of freedom, so maybe not just along the axial direction here, the horizontal direction, but maybe also the vertical direction, and there might be a rotational stiffness as well. There is no dependent degrees of freedom. This thing behaves just like a regular spring element, where you would just have stiffness values that describe the behavior or the relationship between those nodes moving relative to each other. So for example, you might specify the stiffness in the x direction at 100,000 pounds per inch, y direction 20,000 pounds per inch, and rotational stiffness at 5,000 pound-inch per radian. All right, so now that's a bushing element. Now we're going to get to the main subject of this presentation, which is end releases. And so with an end release, what that is we take our frame elements joined together. Now they have a single node that they share, and at that node we might specify that one or more of the degrees of freedom can be released. In other words, the stiffness related to that degree of freedom is released. And so for example, if we had the hinge that we drew on the first slide of this presentation, now it might be node A. There's element 1, there's element 2. We might release the degree of freedom on element 1 at node A, the rotation degree of freedom specifically, and if we did that, that would create a hinge joint. So now the question is, well, how do you do that? And I'm glad you asked, because we got a lot more of this presentation to cover that. So we're going to go ahead and start with the frame element, where we have our translations and our rotation at each of the nodes. And let's say that we have our original frame element stiffness matrix in the frame element coordinate system. And so we've seen this before. We're going to start from here. This is where we start. And then we're going to acknowledge that we want to release some degree of freedom. So just as an example, we're going to say that we want to release this moment and this rotation at node 1. In other words, creating a hinge at node 1, the left side of that element. And so if that's the case, well, we know that we do not want to transfer any moment. So we would say that this would be equal to 0. Similarly, we know that this could be any value, and it should not have any effect. That rotation can be any value it wants, and it should not have any effect on the rotational stiffness. And so we'll go ahead and erase our original values, and this would be about the form that this frame element stiffness matrix would transform into if we were to release this degree of freedom. And so first thing we do is we have a row of zeros. And we have a row of zeros because we know that this moment value needs to be equal to 0. So we're just going to set that row equal to 0. So these values can be whatever they want, and that moment will still be 0. Similarly, we'll create a column of zeros. And the reason that we have a column of zeros is because this rotational value there, theta 1, can be any value, but it should not affect any of these forces or moments in that force vector. And so this column would correspond to all the values in the matrix that would multiply against that. So we just set all those equal to 0. And the rest of that is what we want to figure out. We want to figure out what is in the gray boxes. And so now is this a meditative, we'll just kind of let this thing play out. I think it's fun to look at. All right, we're done. Let's move on. So we do this by splitting up that original matrix equation into released and retained components. All right, so for example, we want to release degree of freedom 3. That's what we had on the previous slide. So that's the rotation corresponding to node 1. We go ahead and start with our original matrix equation. And here we select the component of the force matrix, or pardon me, the force vector that is released. We want to release that third degree of freedom. Similarly, we select the element within our displacement vector. That's the theta 1, or rotation at node 1, and that's going to be our released component. We do the same thing for our retained degrees of freedom, right? So we're just splitting these vectors up into our released and our retained portions. All right, just like we did that with our force vector and our displacement vector, we're going to go ahead and do the same thing for our stiffness matrix. All right, so that's what we had from the previous slide. We're going to go ahead and start with what portion of the stiffness matrix is released. And so it turns out to be just this element there in the center. We look at the retained portions, and so that's all the rows and columns that do not have degree of freedom 3 in it. So we'll go ahead and put boxes around those. Well, now we have these other portions here, and so we'll create some naming for those as well. We're going to call this vertical one, we'll call it K-release vertical. Seems pretty straightforward. It seemed like a straightforward naming when I wrote it earlier. And similarly, we'll say this is our released portion of the stiffness matrix that's horizontal. Okay, so now we just kind of partitioned our stiffness matrix, our original version of the stiffness matrix. Okay, so now from those we're going to create two separate force equals stiffness matrix times displacement equations. All right, so it's the same overall, or it stems from the same overall general force stiffness matrix displacement equation for a frame element, but we just split it into a retained portion and a released portion. And that's all we're doing. So this is just matrix math. It's the same version as the regular matrix multiplication. We're just kind of splitting it up according to the subcomponents of the matrix that we defined in the previous couple slides. All right, well, first thing we know is that this portion, F release, must equal 0 because no load can be transmitted through a released degree of freedom. That's what we said at the start, where we said, hey, we're going to release the moment at node 1. The moment has to have a value of 0, right? Like what type of moment can be transferred through a hinge joint? Not much. Okay, so we know that must be equal to 0. And if that must be equal to 0, what we're going to do is we're going to take this equation and we're going to go ahead and solve for our released portion of the displacement vector. And then we go ahead and plug that portion back into the retained equation. All right, so let's go ahead and see that in detail. There's what we wrote on the previous slide. We're going to solve for that released portion of the displacement vector in the released equation. So it looks something like this. All right, that's just rearranging it, and you'll notice that I took that force, or the released portion of the force vector. Well, we got rid of that because it says 0, so we didn't need to include that. All right, so now we have this type of relationship, and we can take this type of relationship and plug it into that retained portion of the force stiffness matrix displacement equation. All right, so that's what we have here. You'll notice that we just rewrote it, and now we're just going to go ahead and take that portion and plug it in there. And if we go ahead and do that, we end up getting the following relationship, all these different vectors. The beauty about using a program like MATLAB is you can just do this and it will automatically come up with the right response. And this portion here, that answers the question we had from a couple slides ago. What's in the gray boxes? That's what's in the gray boxes. All right, so let's go ahead and write it out one more time using that example with degree of freedom being 3, degree of freedom 3 being released. We'll go ahead and write out our stiffness matrix equation here. All right, well, we know once again that the moment needs to be 0. So we go ahead and put everything in that row equal to 0. We know that this value can be any value, and it should not affect any of these loads. So we'll go ahead and put our column of zeros there. And then we'll go ahead and draw a different variation of the what's in the gray boxes. And we'll just go ahead and write the equation for the gray boxes. Keep in mind that in this case, our retained degree of freedom stiffness matrix, right, that would be 5 by 5, right, because it removes degree of freedom 3. And so sure enough, if we were able to combine all those gray boxes, we would have a 5 by 5 stiffness matrix, and we would get that by using this equation that we have here. All right. So with that, we have some reflective questions. The first reflective question that we have is, what do end releases represent? The next one we have is, can more than one degree of freedom be released at one end of a frame element? The next one is, what are the similarities and differences between the different types of joint methods we covered earlier? So that would be end releases, multi-point constraints, and bushing elements. And then we have, what does the frame element stiffness matrix resemble if the rotation is released at both nodes? All right. Now, normally this would be the end of the presentation, but I couldn't help myself. We have one more bonus question. And that is, let's assume that we have two frame elements joined together, same coincident node here. We have a fixed end on the left side, fixed end on the right side, a point load there in the center. And we're going to go ahead and assume that degree of freedom 3 is released from element 2. So that's the rotation at node A. It's released from element 2, retained at element 1, right? So element 1, that stiffness matrix would resemble just the original frame element stiffness matrix. Stiffness matrix for element 2, that would be modified to account for degree of freedom 3 being released. So we would expect it to deform something like this. Remember, this represents a hinge joint now, right? So let's get to the question. The question is, which rotation at node A will be given in the output? So after you run FEA, will the rotation at node A be what you would get from element 1? Notice how this would be a negative rotation. Or would it be the answer that you would get from element 2? That would be a positive rotation. So which one do you think it would be? All right, and that, I believe, is the end of the presentation.